Welcome to Data Science with EJD. In this video, I'll be looking at a capstone project on the supervised learning pipeline for sports prediction. We've been doing all kinds of, we've been doing all kinds of supervised learning stuff, talking about classification and regression and all that. Then we've looked at different aspects like deployment, like the metrics attached and things like that. Here, I want to use this as the last video for supervised learning. So after now, I'll be going into unsupervised learning where we talk about clustering and all the dimension reduction and all and things like that. All right, so come along. So the focus is on sports prediction. Let's see. Um, Sports predicting sports match outcomes, like whether there's a win or loss or draw, is a classic supervised learning problem with applications in betting. Well, I don't subscribe to betting for sure, right? But for team strategy and fan engagement. So this project aims to develop a reproducible machine learning pipeline that automates data preprocessing, feature engineering, training, and evaluation to predict match outcomes effectively. This can help, like if you're a team manager or you're a fan manager and things like that, or you're a team strategist. So being able to see the performance. I mean, data can really help you to predict some things. Of course, at best they are predictions; they are not reality, right? But I mean, with past data, you can predict with a level of confidence. All right. So talking about project objectives now. So we want to build an end-to-end machine learning pipeline for sports outcome prediction and handle categorical and numerical data effectively. This is a very big deal when we do machine learning projects. So categorical data needs to be handled effectively so you can get a model that performs very well. Then you need to evaluate multiple models and select the best performing one. Implement hyperparameter tuning for model optimization. Prepare the pipeline for deployment, e.g. integration with web app or API, if you're going that far. So data understand. Let's understand the data we have here. So typical features collected from historical matches might include. So from historical matches, maybe you're talking about two teams playing and they have always played for the past 30 or 50 years. So you can collect all the information. Like you want to see which in the match which team was the home team. So what's the name of the home team and it's categorical, right? Away team, name of the away team, the type is categorical. Home team rank, right? Current rank of the home team, maybe their position on the table or something like that. Away team rank, numeric. Then you have home goals last five matches or so. So goals scored by home team in last five matches, numeric for sure. Away goals in the last five matches. So goals scored by a away team in last five matches, that's numeric. The match outcome, that's the result of the match, whether a win or a loss or draw for the home. So the focus is on the home, right? So if you see a win, that's for the home team. If you see a loss, that's for the home team. If you see a draw, of course, that means both of them had the same goals. And the type of data here is categorical in nature. So that's the kind of thing we're dealing with since we are talking about sports prediction. So let's talk about the problem type. Of course, it's a supervised learning problem and it is multi-class classification, right? So multi-class in the sense that I think we are classifying into into whether there's a win or loss or draw. Which of these three is going to happen in a match that is coming in the future or something like that. So then let's look at data preprocessing and feature engineering. So of course, the first thing we want to think about here is handling missing values. So we want to impute missing numerical data using mean or median if necessary. For categorical data, you can impute with mode or introduce an unknown category if you like. All right. And then you can also do part of data processing is encoding categorical features. So you can use one hot encoding for team names and other nominal features, right? Like for team names now, you can say maybe the first team is team one, the second team is team two, and things like that as you like it. Then we can also have feature scaling. So you can scale numerical features using standard scalar, where mean is zero and variance is one. Scaling is all about making the variable, making this data such that it is normally distributed with mean zero and variance one. And then you have the feature creation. which is optional. So you can do rolling averages if you like, e.g., average goals in last 3 or 5 matches if you want. You can do head-to-head win rates between teams. You can do binary feature for home advantage. So things like that. Then exploratory data analysis. You can visualize distributions of numerical features, analyze class balance and target variable, generate correlation heat maps, review feature importance from preliminary models. So those are things we can do. Then you can also do model selection and building. So some models to consider in this case, since we are trying to predict whether a team wins or loses, whether the home team in particular wins or loses or draws. So we can look at logistic regression, which is simple and interpretable. We've done this in the past, and the use case is baseline. That's a basic thing you can do. Then you can use random forest, which handles categorical data well, and it is robust. It has medium complexity, and you can go very ballistic, so to speak, and you talk about gradient boosting like XGBoost or LGBM. So it has high accuracy and handles heterogeneity, and the case is when you need to do advanced modeling. Then neural networks can capture complex feature interactions, and large data sets with deep relations will be use cases for this. Okay, so depending on the how big your data is, so model evaluation metrics now, of course, since it's a classification problem you're doing, you need classification metrics like accuracy, precision, recall, and F1 score, which is especially for imbalanced data sets. Then you need confusion matrix for visualization and cross-validation scores. Then we can also do hyperparameter tuning to make the model better. So you can use grid search CV. We've done this in the past, or randomized search cross validation for optimization. So you can tune parameters such as the number of trees, assuming that you're bringing you're aggregating decision trees to use a forest estimator or something like that. So the number of trees, the tree depth, the learning rate, and the regularization. Talking about whether you're just talking about ridge or lasso. Then after you've done all that, you need to do your final model and deployment pipeline. So you combine preprocessing steps and best model into a single scikit-learn pipeline, and then you save the final pipeline using joblib or Pico. We've gone through all of this. So for prediction, you can load the saved model, and then you use .predict on new or unseen data. Okay. In 10, future work improvements on all these things, right? So you can integrate external data sources, e.g., weather, injuries, player stats, if you want. Like if you want something more robust, you can integrate what was the weather condition. Can all this also help in predicting the winning team? What about the injuries, the player statistics? Then you can also experiment with ensemble methods. I think we did some ensemble methods like trying to remember all those bagging, voting, boosting, things like that. Then you can build interpretability tools using Sharp or Lime. Then you can deploy as a REST API using Flask or Fast API for integration into apps. So if you want to make this prediction thing into an app, those are things you may want to consider. So some references, you look at the scikit-learn documentation. If you click on this, it takes you to the scikit-learn website, and where you can see the whole documentation about scikit-learn, talking about classification, regression, supervised learning, then clustering, dimensionality reduction, and all that for what is it called now, for unsupervised learning, which you're going to see pretty soon, right? Then we've talked about model selection, pre-processing, and things like that. uh you know then academic papers on sports analytics and machine learning can also help. Then you can look at cargo sports prediction data sets. So data sets related to all this can be really helpful. So I want to put the line numbers for easy referencing. Now so all these stories I've told now we go into the coding aspect of things. So to implement this now, we are doing a supervised learning job one that we are trying to, it is a classification job. So you need to know the right models and all that to use. And of course, from experience, the best model we've seen for classification jobs is random forest classifier, right? So first thing you want to import necessary libraries, the fundamentals, pandas, numpy, matplotlib, seaborn, then joblib because you're going to save you want to save your model later for deployment. Then of course, now for the actual machine learning thing, you need all the scikit-learn stuff. You need to the train test splits. Since you're going to do hyperparameter, you need grid search, severe randomized search, cross validation. Then for preprocessing, you need standard scale and one health encoder. Then you need column transformer, pipeline. You need a pipeline, right, which automates some processes. Then you also need random forest classifier as your model. Then you need metrics like classification reports and confusion matrix. So of course, don't forget to run that. I run that now, and it takes a bit of time. And then once the number shows, then it's done. Yeah, that's done. Then the next thing is to load and inspect data. So in this case now, the data imputation is manual and it is taking the form of, we are creating the data as a Python library, no, Python dictionary, right? Where you have a key value pair. So the key here are all these home team, away team, and the value are all these Python uh, Python lists actually. So away team, you have team A, team B, team A, team C, based on the matches we are looking at. So you have all of that. So in particular encounters, you have the home and away team. So team A, team B for the first one, team B, team A, team A. So the first one is are the home teams, right? Whatever comes as the home team. So team A, team C, and it goes on like that. Then, so for each of those encounters, you can have the home team rank and the away team rank. So like their position on the table, right? So you have one, two, two, one, and all this. Then you have home goals, uh, home goals in the last five matches for the home team, and away goals, in the last five matches. Then you have the match outcome, or the win, loss, and draw kind of thing. And then in line 70, you're making that into a pandas data frame. And here we want to visualize the data in line 20. So if I run that, you see this now. So the so we have 15 reports of 15 games, right? So to speak. So you have team A, team B, and home team rank. For team A was number one on the table, while team B was number two on the table. Then home goals in the last five matches. So the goals of the home team in the last five matches, that's eight. Away, that's five. And then the outcome is win. That's win for the home team. So whatever you see here is for the home team, right? So team B, team A also, they also met at some point, and team B also lost. I mean, team B actually lost in this situation. So it's like when Team A played Team B in their home, they won. When they went to play Team B in their own home, Team A now lost. So something like this. So you have this 15 stuff like this. So we have this. So, I mean, you could also upload a JSON, CSV, or Excel file as we've been doing, starting from data analysis. So now we want to define the features and targets. So you can see in here we have, of course, we could do exploratory data analysis, all this df.info. Okay, maybe I should even, okay, well, I mean, we can see this clearly already. So match outcome is the last thing here. So we want to now define features and targets. So features are the input, while the target is the output. So here we drop the match outcome because that is our target, right? So we want to determine match outcome based on every other thing, based on all the home team, away team, their ranking and their goals in the last five matches, right? So for line two, we drop match outcome. So and then in line three, we now assign the match outcome variable to what to y, the target, right? So we run that. And once we run that, I want to really now see this target. So I run this. So you see the outcome is no longer there, match outcome is no longer there. So we only have the every other thing. So we are determining match outcome based on this or these ideas, based on these targets. Sorry, based on these features rather. Then Y itself is the target, which is the match outcome, and it tells us from the first to the 15th, win, loss, draw, blah blah. So we want to determine whether there's a loss or win depending on previous data. Then the next thing we want to do is to split the data set as we've always done. So X train, X test, Y train, Y test, and then we train and test split. So we have X, Y, test size is 0.25. So it means we are training the data set. We are training the model rather with 75% of the data set, and we are testing with 25%. So in this case, the random state is for the two to make sure we can always reproduce, and we stratify with the match outcome. Okay, so that is done. The next thing is we define pre-processing steps. So categorical columns like home team and away team, then numerical columns like home team rank, away team rank, home goals, and all that. So we have separated them. So these are the categorical columns. These are the numerical columns, right? Categorical in the sense that the columns for home team and away team is either team A or team B or team C, like that. So those are basically categorical. But the ranking and the number of goals, those are numerical in nature. So for categorical transformer now, we now do one hot encoding for all the home team away. So handle unknown ignore. So for numeric transformer, we do the standard scaling for all this to make sure that the data is normally distributed. Then for we now have the preprocessor. That's column transformer. You have transformers, numbers, numeric transformer. So the numeric transformer, numeric columns, cat. That's categorical transformer, categorical column. So we do that preprocessing thing. So we run that and it's done. The next thing is we want to create a pipeline with random forest, right? So we have pipeline steps. So preprocessor, classifier is random forest classifier. We put random state equals 42 for reproducibility. So here we do the pipeline. And then the next thing is we now train the model. Since we've created a pipeline, so it will now be the pipeline itself we are creating. Instead of saying model.fit, we say pipeline.fit. So we run that. So the pipeline has been fit. So you have in the pipeline, you have the standard scaling, one hot encoding, and the random forest classifier. All right. So the next thing is, since we've trained the model, we now want to evaluate the model like that, right? So you now have ypred is pipeline.predict based on the test data. So you want to test with the test data, right? Then this will now print the classification reports. Y test ypred, zero division is zero. So this helps to handle undefined metrics. Then you also get the confusion matrix, where you get true positive, true negative, true positive, false positive, and all of those things in a matrix form. So you run this, and this is exactly what you get. So for the classification reports, you have all the precision, recall, F1 score, and the supports, all that. So you now have the average values of all these things. So in all, you have the accuracy to be 0.75%. That's 75% confidence in the prediction, right? Then you have the confusion matrix in this case, talking about the win and the losses, right? Then now, based on this now, we've got the accuracy to be 0.75%. Now, but the issue is, when we do hyperparameter tuning, can we try like parameter grid, the number of estimators, 50 or 100, maximum depth is it none or five? So it will move across this 50 none to 50 none 5, then 100 none to 100 none 5. So it will try all these possibilities. And so yeah, we're going to have like how many trials? That's 2 times 3 times 2. 2 times 3 is 6 times 2. That's like 12 possibilities. And to now find out which of these combinations works best. Then we have the grid search. Now, since we are talking about hyperparameter tuning, so grid search, we do that on the pipeline with the parameter grid here. The cross validation is 3 and the scoring accuracy. So with this cross validation, maybe we are even talking about 12 times 3, which is 36, right? Then grid search will be fit to the train model, X train, Y train, and then we try to get the best parameters from the grid search, and we also get the best cross validation score. So we run this, and it takes a bit of time because it's doing like 36 trials or something like that. So with this now, the best cross validation is 0.639, and then you see the maximum depth. So the best combination is the best combination is 50 here, none here, and 2 here, right? So those are the best parameters, and the best cross validation accuracy is 63.9%. That's roughly 64%. So then the next thing is we want to test the best model. So best model is now grid underscore search dot best estimator. Then why the best predicted value of our best model dot predict x test. And then it gives us classification reports and all that. So we run this again. So you see everything is now looking like perfect. So the accuracy is 100%. Everything just works excellently well for the best for testing the best model now. So having done all of this, you can now save the model as a pipeline. So first of all, we are saving this as sports underscore prediction underscore pipeline the job lib. So let's check my folder with the folder I'm working with in this situation. Okay, so if the folder is on the desktop, this is math with EJD, data science with EJD, and so far we don't have any sports thing here. So once I run that now, I just run this to model pipeline save to sports prediction.pipeline.joblib. So we just come here and then, this is just created 3:29 a.m. just like here. And then we have that. So with that, now we are done with that capstone project. So in summary, this capstone project demonstrates a systematic approach to understanding the data and problem, preparing features, right? Training and tuning models, evaluating performance, and serving a deployment-ready pipeline. So this approach can be extended to real-world sports data sets with richer features and more advanced models. So if you want to maybe bring in weather, player statistics, coach statistics, and things like that, you can actually bring all of them in. So this runs you through the whole flow of the whole machine learning flow in this situation. All right, with this, I come to the very end of this video and the end of supervised learning. So from the subsequent video, I'll be talking about unsupervised learning, right? So you don't want to miss out on any of that. So let me know how helpful this is for you. And if there's something you like me to try out, feel free to let me know. If you have subscribed, thank you so much. If you have not subscribed already, be sure to do that right away and hit the notification bell so you can always get alerted each time a new video is released. And my channel now has membership, so you can join as a member, explore the features there, and you can get some special benefits by being a member, right? Um, Also, like and share this video so that many people can have access to the great content I have going on here. Till I come your way again, keep doing data right. Bye.